Yo, I didn't like that. I just did not like that. Wasn't comfortable with that. My blunts burn hard and my haters dream on. Here's a little story about Bernhard Riemann, living your life after your mother's gone. And it goes a little something like this. Son of a pastor, but when young Bernie speaks, sometimes it could spell a disaster. Yet as a child, the master of the math, Bernhard Riemann, yeah, he always finds the answer. And forget a teacher, Bernhard nearly turned to becoming a preacher. But when Bernhard met Gauss, it was on. Mathematics at ages like Dom Perignon. This is the story of Bernhard Riemann, and I'm on. Gauss was on Riemann's habilitation committee. 3 topics to choose for demonstrating he's witty. Would it be electricity or that hydro flow? Because the Riemann integral was all ready to go. Riemann's pre-computed, an ace in the hole. But Gauss would pull a fast one, cause you already know. Gauss is the expert and he picked topic 3 on hypotheses which lie at the foundations of geometry. Riemann went home and flipped what might have been dismay into the math for relativity we know today. Riemann paid for what we get for free. Of constant curvature geometries, there's 3. He successfully defended and was getting it on. This is the story of Bernhard Riemann. Now not 2 months till he turned 40 years old, he laid his head down before his word turned cold. His wife kept praying as the end drew near. When they started Our Father, Riemann was still here. By the time they finished, thy will was done, and Riemann was already in kingdom come. His life as a mathematician was a way to serve God, the type of math that make the mother names applaud. This was the story of Bernhard Riemann, and it's gone. So yeah, that's like the big surprise of this whole episode, is that I am going to fill in the gaps and go starting from things that have been in the reading that I've done so far in the past 32 episodes. I'm going to use those as like the first principles and compute my way to Riemann's result here. And we're going to hopefully then be able to like wrap our heads around like, what is this 13 pages about? I'm just going to type this out here. I have this little template, as you can see. The work of a reader left for dead, to fill in the gaps of Riemann's Über die Hypothesen welcher der Geometrie zugrunde liegen as an exercise. Anthony makes videos. I typed out this template yesterday. Yeah, I just want to do these more like off the dome, less structured, less like I'm, doing a lecture where I'm reading from lecture notes, and just make it like vibing like a stream, which is kind of like how I advertise these, how I initially thought of setting about doing these, but, I'm just, hitting record, and we're just going to upload this with minimal editing. So hope you guys enjoy this so far. You guys, we are coming to the finale, the grand finale of calculations, where we're about to connect the dots and the gap will be basically filled, and we will have connected to, it's now referenced as line 62 here, which is straight out of Riemann's habilitation thesis, and we're about to get a calculation that connects to that. All right, and there we have it. All right, salut tout le monde. Welcome back. It's been a while this year. It's been a rough go at the whole streams, but in the last one, it was like 2 weeks ago, I announced that I had this whole new streaming setup, kind of, and it makes the whole editing and throughput of making these videos a lot easier. But I'm going to be honest with you, okay? So I kind of mentioned this last time, which was on the Bianchi identities. Shortest section in the book that I've been reading out loud for you guys, Differential Geometry by Erwin Kreyszig, okay? We're in chapter 7, last section, 74. Shortest section. It's like almost a full page. Just doing a quick proof of what are known as the Bianchi identities. And I related that to general relativity, which is kind of like a sub relate, not like sub as in like subset, maybe as in like secret topic. Like this whole stream series has been about differential geometry, but it's secretly also been about general relativity. So I showed or mentioned kind of how the Bianchi identities in general relativity are this sort of like conservation statement for gravity, and there's this whole mantra, the boundary of a boundary is zero kind of thing. And I kind of had this realization though. I was like, technically this isn't what you might call differential geometry. This might be what you would call Riemannian geometry. And so where's this all going? What's been on my mind as I've been reading all this is the work and the life of Bernhard Riemann himself. And I think about how in research in the sciences, for example, it's really important to always go back to primary sources. And for math, you kind of take that for granted because it goes back to like Euclid doing geometric proofs. Seeing is believing. If you could just show a geometric proof, if you could show a proof of some theorem, then you really don't have to like say, oh, this is, the work of some guy who did an experiment under these particular conditions and he had these materials, etc., etc. It's like you can just see the proof of a theorem and you can run with it. Although there is historical context, like, we start naming theorems, obviously after big names like Gauss and all this kind of stuff, Cauchy. But I decided to go back and look at Über die Hypothesen, welche der Geometrie Gründe liegen. Did I say that right? Welche der Geometrie Gründe liegen? Yeah, I don't speak German. That was my best attempt at the pronunciation. On the Hypotheses which lie at the basis of geometry by Bernhard Riemann, 1854. And the reason why I decided to actually dive into this, it's like, I also think in my mind that I should be reviewing fundamentals of topology, for instance, or before doing a deep dive into Riemannian geometry, maybe I should circle back on differential geometry or just smooth manifolds before I revisit things like geodesics and all of that in quote-unquote higher level of Riemannian geometry. But I was like, I couldn't resist. I looked up the original, what kicked off Riemannian geometry. So I find online on the Hypotheses, which lie at the basis of geometry, PDF. I open it up, and it's 15 pages. And I think to myself, this has to be a joke. Are you joking me right now? This is a habilitation thesis. That's only 15 pages. No way. I open it up. Okay, the last 2 pages are a synopsis. So this is really like 13 pages. And I'm like, wow, that's pretty intense. This is just my recollection of my first take on it, right? Because I've obviously gone through this with, multiple times, taken notes in the margins, and we're going to get into this, okay? You're going to see where I'm going with this. I'm reading through this, and it's 1854, right, at the time that this is published in Germany. So Hegel has already been gone for a few decades, but you kind of get the same feeling. I mentioned a few episodes ago how people now will accuse Hegel of being like the epitome of muddled thinking, because when you read stuff like, can we see this over here? Hegel's Phenomenology of Spirit, okay, you crack that open and you start reading the preface, and just like a few sentences in, you're already like, wow, this is not exactly like the cut and dry, math, science articles that you would just like Sci-Hub, download whatever from Nature, Science, pick a journal. This does not sound anything like that. you know, because it talks about things as like measure relations, magnitude relations, notions. That's a thing that Hegel really was perhaps the master of using, is sort of like going in between a notion, a concept, and an idea. Like, what's the difference between a notion, a concept, and an idea, right? And so that was my first impression when I was reading this. And you go through and, okay, let me pull it up on the screen now. This might be a good time to go into this. So we're going through here, and let's just go to the end, the synopsis. Hopefully we can all see this. Okay, so like there's two main parts. First, notion of an n-ply extended magnitude. N could be 2, so it's doubly, or n could be 3, triply, 4, quadruply. This is kind of like where we get Riemannian manifolds, where we have this n-dimensional generalization of a surface, essentially. But then it comes up with the problem of how do you measure lengths, angles, and angles on this n-dimensional analog of just like a general surface. And this surface is going to be affected mathematically by notions of stretching and bending. I'm getting a little bit ahead of myself. The second part here, measure relations of which a manifoldness of n dimensions is capable on the assumption that lines have a length independent position, and consequently that every line may be measured by every other. It's like we have lots of verbosity here, but then we come down to section 4. Flat manifoldedness may be treated as a special case of manifoldednesses. Okay, I'm just going to say that again. Flat manifoldnesses may be treated as a special case of manifoldnesses with constant curvature. That's definitely not the way I feel like things are described. Things as having a manifoldness, and then the plural of that is manifoldnesses. Okay, anyways. Just saying that flat manifolds are a special case of constant curvature, where curvature in that case is 0. The constant is 0. K equals 0. And okay, as it turns out, alright, we're going to scroll back. Boom, right there at the end of section 4. This is literally the only equation, expression, math in this entire thing. So it's like you're telling me that this guy, Bernhard Riemann, wrote this, basically it's like a postdoc thesis, if you will. It's only like 13 pages typed out now, today, 2025. Who knows what the typesetting was like in 1854. Still, it's really short. It only has one expression in the whole thing, okay? So today, I am going to fill in the gaps, and we're going to figure out what does this mean here? We have 1 over a denominator of 1 plus basically alpha over 4 times the sum of all x squared. Then this fraction is times the square root of the sum of all dx squared that we have. And this is something that can absolutely be handled from what we've learned so far, read so far in Differential Geometry by Kreyszig, okay? So, oh my goodness, I still have a typing test here. We're going to do a little ASMR keys audio here with the extra microphone. So, I'm just going to type this out here. I have this little template, as you can see, the work of a reader left for dead, to fill in the gaps of Riemann's Über die Hypothesen welcher der Geometrie zugrunde liegen as an exercise. Anthony makes videos. I typed out this template yesterday, but we're going to kick it off today, and the date is going to change. yeah, we're going to go into stereographic projection, and there's a lot to talk about here. So, all right. So the result that's going to be worked out here is to derive... Yeah, and I'm just going to be typing out my notes. That's the big surprise. I'm going to go back to this. So yeah, that's like the big surprise of this whole episode, is that I am going to fill in the gaps and go starting from things that have been in the reading that I've done so far in the past 32 episodes. I'm going to use those as like the first principles and compute my way to Riemann's result here. And we're going to hopefully then be able to like wrap our heads around like, what is this 13 pages about? How does this, why is this math that people still care about, that they still write books, make money off of, ostensibly? Like, we've got Peter Peterson's Riemannian geometry book. He wrote hundreds of pages on the subject of Riemannian geometry, obviously, and it all kicked off from this like dozen-page long paper, basically. So it's like, and there's only one math expression. Like, what is going on here? So yeah, I'm just gonna be typing up my notes that are the answer to that. So there's probably going to be stuff that's maybe incorrect, and we're going to leave that to you and the audience to find out. So we've got the author, the reader, and the audience of the people watching him do this exercise. So let's get this. The result worked out here is to derive a metric. Oh man, I didn't even go back to typing. Okay. Now we're looking at the typing. So metrics, this basically just goes back all the way to Pythagoras. I mean, we call these spaces Euclidean, but what does that mean? Okay, you could have rectangular coordinates, so the axes are defined by perpendicular lines, basically, and everything is flat. So you're not doing this on a sphere, say, because critically you need, there's like the parallel line postulate, where if you have two lines that are at right angles, then in either direction there's no point that they're going to intersect. But also, kind of like really closely related to that, you have the Pythagorean theorem, right? So x squared plus z squared equals c squared, two legs of the triangle squared, add them up, that equals the square of the length of the hypotenuse. But, we're really going to take that to the nth dimension, literally, when we're using n-dimensional Riemannian manifolds. So when you're in n-dimensional Euclidean space, instead of saying, okay, we're just going to stop x squared plus y squared equals z squared, we're going to have n terms on the left-hand side, going from x squared plus y squared, boom, all the way out to n. And yeah, so anyways, metrics. For a surface parametrized by, let's say, just u and v to start off with, the metric is given by ds squared, which is equal to, we're going to throw in g, which is going to be, generally it's a metric, but we first saw it in the Differential Geometry Kreyszig book as the first fundamental form, right? Let me type this out here first. Gij dxi dxj. So, I mean, I don't know. I have the next section is called curvature, but I guess, I don't know, I might as well bring it up now. So it's like, we're looking at this, I've defined this metric on a surface parametrized by just two dimensions to start off. We're going to call this metric ds squared. And, I just kind of like brought up that stuff about the Pythagorean theorem, right? And because it's like, why would what we're using to measure lengths, and then eventually we might use those lengths to come up with areas. We might look at, angles between these lengths eventually. So it's like we have to start off somewhere. We're going to start with a metric. Why is this metric involving something squared? Okay, I'm trying to associate this with the Pythagorean theorem, right? Because we're in Euclidean space, so we want right angles, triangles, these kinds of things to always work out in really predictable ways, let's just say, even as we start to generalize to higher dimensions. Because, okay, obviously I'm going to address the elephant in the room. We've got this picture here to the right, the mid-sagittal section of the stereographic projection of a point called P. Okay, that's basically saying we're looking at a three-dimensional unit sphere, let's say x squared plus y squared plus z squared equals 1. I don't know if we can zoom in maybe a little bit on the MATLAB legend going on here. Okay, that's what this blue circle is here. Then we take a slice. It's like if the unit sphere were your head, then we do a buzz saw straight down the middle, and then you're just you open up, and then you look at the inside there. That is the circle. That is the picture that is right there. That slice of the unit sphere, okay? And I'll get into all this in a sec, but look at how we have this point N, and we have this point P, and we have the origin. That makes a triangle, right? Similarly, we have this P, P prime, and P underscore triangle. So if you start doing all this stuff on curved surfaces, things are going to go all screwy-dewy on you really quickly. So, that's just why we're going to start with Pythagorean. We're starting to, pull things out of the ether, ds squared, okay? And we have dxi, dxj. What does that mean? Okay, well, we brought this idea of principal curvature, which is when you're on a surface at a particular point and you have tangents going off in different directions. You want to look at the directions where those tangents are the greatest in magnitude, or that's to say, what are the directions going away from that particular point that are the steepest. And usually you define these so-called principal curvatures so that they're at right angles to each other, let's say. So when I'm talking about this surface parameterized by u and v, we want to have picked out u and v are these vectors on the surface that are pointing in these so-called principal directions where those tangents are maxed out, basically. So that's not to say, you could be on a surface of constant curvature, okay? But, we have to have some little bit of generality in here. So you're going to pick dxi and dxj so that if we have the smallest rulers, so that you could take that ruler to any other point on this manifold, and that ruler is the smallest length choice that you picked is not going to be affected by any stretching or bending that you may encounter on the rest of this surface, okay? And Gij, this first fundamental form, is like you looked at whatever point, you found those two infinitesimals for these principal curvatures, dot product together, basically. And how is that different from if you had in your embedded Euclidean space two analogous vectors, let's say, and you dot product those together? What is that scale difference? That's G. Okay. So in 2D, i.e. Euclidean or Pythagorean, this would just be ds squared equals du squared plus dv squared. Whoops. For a plane. For surfaces of non-zero curvature, we will consider scaling the flat metric by a conformal factor. And I went over this several episodes ago, but conformal mappings, conformal transformations just mean that when you go from your input to your output, you're preserving angles. We'll say a general conformal factor here. So we have ds squared equals e to the 2u sum dxi squared. And you're like, okay, why did I pick e to the 2u? Well, I could have also said, whoops. I could have done this. Lambda, okay? Or even like lambda squared, something like that. But we're just going to toss around e to the 2u because, I mean, I hate to make it hand wavy, but it's like in the end, in order to get the stereographic projection formula, which is basically, if you haven't figured out and you looked at the result in Riemann's habilitation dissertation, that result is in the form of the formula for stereographic projection. So then, you know, you could plug in that satisfies as a solution Louisville's equation, the PDE that I'm going to type out here in a second. But basically, this is going to go from the other direction, where I start from Christoffel symbols, straight from basically the equation sheet from the back of Differential Geometry by Kreyszig, and we're going to go forward to then get the result in Riemann's habilitation thesis. Those are the gaps that I'm filling in here. So I started off basically using lambda, because this ds squared equals lambda sum of dxi squared. This is first given in the book as ds squared equals basically lambda du squared plus dv squared, and it's all like, this is the differential equation or the relation for the metric or the relation for the differential arc length on the surface, whatever you want to call it. This is for isothermal coordinates, and this was what, like section 62 or something, and there was like the one problem at the end of the section was pick for lambda a plus b, where a depends on u and b depends on v. But I was like, okay, we're just going to keep this more general, work it out with lambda. And then I get to the end, and it's like log of the stereographic projection formula in a general form, where it's like, oh, light bulb moment, if I would have just started off with lambda equals e to the u, and then also, if you didn't realize, okay, this expression right here, in the numerator, basically, right, we've got the square root of the sum of these dx squareds. And on the denominator, we have 1 plus alpha over. Okay, so what's implicit here is this is equal to ds, basically. And a lot of the time you're working with ds squared. So when I, work this out the first time, and I'm like, oh, if I would have started off with e to the 2u, that justifies taking a logarithm, and then how do you go from ds to ds squared? And the other thing is that there's a lot of simplification of some of these calculations involving especially like the stereographic projection aspect of things, where it's easy to use complex numbers. And the exponential function is analytic in the complex plane. So any input from the complex plane, which is basically as dense as r squared in terms of points, it converges. The function e to the whatever you put in there is going to converge everywhere in a complex plane, which gives you infinity squared options that you can put in there. So it's like, if you're going to put anything into that lambda, that's a pretty versatile function that you could put in there. More versatile than like a general polynomial, because some would argue that is a general polynomial if you do the power series expansion of the complex exponential function. Anyways, I don't know. I put this as another item for the geometric context. This is more like topological context, but nowadays you think of these, how am I going to say this? You want these manifolds to be locally Euclidean, but that also has to do with things such as being a Hausdorff space and there's a second countable basis for the underlying set. Yeah, those are more of topological qualities, but I don't know, I feel like I've already hammered on a lot about locally Euclidean. Okay, curvature. What am I going to say about curvature? Yeah, I'm trying to do these just off the dome for you guys. Actually, hold on, I'm going to do this. Yeah, I just want to do these more like off the dome, less structured, less like I'm, doing a lecture where I'm reading from lecture notes, and just make it like vibing like a stream, which is kind of like how I advertise these, how I initially thought of setting about doing these, but, I'm just, hitting record, and we're just going to upload this with minimal editing. So hope you guys enjoy this so far. Oh yeah. And this is an update. I haven't looked at how many people have responded to the survey so far. I'm going to put it in the description of this one and leave it up for just a little bit longer, but then probably at the end of this month I'm going to decide, well, that's in 3 days, so like the beginning of next month will be probably when you see it, when I get around to filming it, let's be honest. Yeah, the beginning of March, I'm actually going to decide who is the winner of the free Figure 69 Cone Anthony Makes Videos t-shirt. And I don't know if there's enough people to start the Discord officially. I might start the Patreon though. But I did notice that there were a few responses, but like a rating scale of like 1 to 10. How interested are you in like my material overall was something like the question, I think. But I put, for 1, it's like I'm just kind of like whatever, just a passerby basically, saw your stuff, curious about it, couldn't care less basically. 10, I said you would be willing to join a cult if I started one. And at least 2 people said yes, that you would be interested. So this is shout out to any of you who answered yes. Ask yourself if I, Anthony, showed up to wherever you are soon, and I was like, all right, are you ready to join my cult right now? Let's say that you now are receiving notice. Consider that your formal notice that might happen. Ask yourself now, what would you do to prepare yourself now, knowing that I'm going to show up and be like, hey, it's time to actually join the cult? What would you now do to catch up, basically? Like, for instance, would you now, today, you've heard this in the video and you're like, oh boy, Anthony's going to show up. I need to prepare by going to the gym. I need to sign up for jiu-jitsu because maybe Anthony's going to hit a takedown on my ass or something like that. You never know. Maybe you need to start reading up on topology. Who knows? But whatever it is, you don't have to tell me, but maybe you should think about that. And some of you who are, obviously did not answer that you would be interested in joining my cult. You say, what is this all about? Well, it goes back to Pythagoras, because Pythagoras supposedly was like into a kind of like math, psychedelic, spiritual cult or something like that. And let me put it to you like this. I've talked also, this is another like subtopic, kind of like how I said general relativity is a subtopic for these differential geometry, Riemannian geometry streams. Another subtopic is kind of like UAP disclosure, because that's kind of like been in vogue lately. And the one guy, Lou Elizondo, has been quoted as saying in all of his sort of like learning about all of this stuff, like over the course of his own life, that it sort of is like a pyramid where it starts off, and on two sides of this pyramid are religion and science. And it starts off where maybe you're standing on the science side of the pyramid, and the pyramid is so big and you're on the science side, you're like, there's nothing else but science. And you could also similarly be on the religion side, but then once you get closer to the top, you realize that science and religion are closer together, and that in fact they basically depend on each other at the very top. And so I'm down with that vibe. I'm also, I'm pretty sure that, well, not pretty sure. So basically, like in past episodes, I also referenced Timaeus by Plato, and how you kind of get this feeling when you read about the ancient Greeks that a lot of these big name guys, Timaeus, Solon, Pythagoras, and all of them, at some point in their maturation, let's say, so before they were just like, Greek men in their 40s, they've been wrestling, they've been doing math, they've been trying to, come up with these city-states, wearing togas, taking baths, doing whatever these guys do, right? At some point before they were the man back then, they traveled to Egypt and learned about geometry, basically. And, obviously Euclid then took it in a new direction. But, I'm like, what if I start a cult like Pythagoras, and it's, people having a more spiritual attitude towards things like math or something? I don't know. There's some stuff I have in mind for this. Because, okay, Bernhard Riemann, did you hear the intro rap for this video? He was the son of a pastor, and he initially, when he was at university, he was initially going to study theology, but then got associated with Gauss and then became a mathematician. But nonetheless, it was in his mind, he had never quit theology. It was by doing math, he was just pursuing theology in a new way, right? So I'm gonna be real with you. So I was reading more in depth, actually reading through Über die Hypothesen, this translation, of course, so because I haven't read the primary source in German because I don't speak German. But I'm going to be honest with you. I shed a tear. It was like, reading, say, Infinite Jest for the first time. You read certain passages and it's, you're just taken away. You're just blown away by these things. It's like, being in art museum and you see some painting or sculpture or whatever, and, people are literally brought to tears in museums, art museums and stuff. I feel like psychologically what it is like the beauty of the experience is more than you expected. It's beyond, and that is like an emotionally cathartic thing. I think that's like at the core of what that kind of like art revelatory crying specifically moment is. But it was like I literally shed tears when I was reading this work of Riemann. Here we'll even give a little foreshadowing, because it's like, okay, he goes section 1, he introduces n-dimensional Riemannian manifolds. Section 2, he builds up to this statement of like the stereographic formula is the key to classifying constant curvature and dimensional Riemannian manifolds, basically. And he's just like, boom, I'm not going to show you guys any of the details of how I did it. It's kind of ironic, because where is it over here? Like at the beginning of this, section 1 of it. Okay, maybe it's for the first section. Yeah. So he's like starting to introduce the idea of an n-dimensional Riemannian manifold, except he doesn't call it a Riemannian manifold. We just call what he's kind of like describing here, we call that mathematical object now, in his honor, as a tribute to him, we call it a Riemannian manifold. Anyways, in proceeding to attempt the solution of the first of these problems, the development of the notion of a multiply extended magnitude, I think I may the more claim indulgent criticism in that I am not practiced in such undertakings of a philosophical nature where the difficulty lies more in the notions themselves than in the construction. And he's like, yeah, if you want to read more philosophy, you can read Gauss's work that probably no one's really read besides maybe like people doing a deep dive on Wikipedia about what biquadratic residues are after watching this. I don't know. But basically he's saying like, oh, I'm really not all about the philosophy. But then, okay, we're going to go all the way down here. Section 3 now. Okay, what's this all about? Whoops, I went too far. See, because this is only like a dozen pages. Application to space. He literally introduces n-dimensional Riemannian manifolds, and then he's like, okay, here's this classification theorem, curvature, ties it back to Theorema egregium, basically, from Gauss, who's like the expert on plane curves at this point in time. But then he lays it down in section 3 on basically like a philosophical application of these n-dimensional manifolds to space and time. So it's like he does get philosophical, and so he starts off, here we go, this is for Jordan Peterson. In the extension of space construction to the infinitely great, we must distinguish between between unboundedness and infinite extent. It's like, this is a joke. Is this a Jordan Peterson joke?
The nature of human being is such that it consists of a confrontation with the bounded finite with the unbounded infinite. Those are the bare facts of the matter. The bounded finite with the unbounded infinite. The world of experience as it presents itself to us is literally and not metaphorically complex beyond our capacity to understand.
Surface element. We should obtain an unbounded surface of constant curvature, that is, a surface which, in a flat manifoldness of 3 dimensions, would take the form of a sphere and consequently be finite. So it's like, we kind of get why geodesics would be a concept that's lumped into Riemannian geometry. And this is kind of like also foreshadowing the concept of a Riemannian sphere. But then we can kind of see how it ties back to stereographic projection. Well, I haven't even gotten into stereographic projection yet, but okay, so Section 3. The questions about the infinitely great are for the interpretation of nature useless questions. Is that because Bernhard Riemann thinks of God as the infinitely great, and that is the kicking off point for then going into theology? We shall see, because people like Thomas Aquinas, in reply to that, would say yes. But yeah, it was like, maybe even you can tell just now, the unbounded and infinite extent. And then he just kind of like casually just dodges. It's just like, the questions about the infinitely great are for the interpretation of nature useless questions. And, then he goes on to say stuff about, like, interestingly, microscopes and telescopes. So measurement devices, but specifically ones that rely on light as their mechanism, observing light. And he uses the range of telescopes and microscopes to put like empirical ranges on the nearly infinite extent, shall we say, of these things that he's considered. Then, name dropping Archimedes, Galileo, Newton. Yeah, now it seems that the empirical notions on which the metrical determinations of space are founded, the notion of a solid body and of a ray of light, cease to be valid for the infinitely small. There you have it. So it's almost, it's like, how could you not interpret this as something other than philosophical, right? The question of the validity of the hypotheses of geometry in the infinitely small is bound up with the question of the ground of the metric relations of space. The groundings, perhaps. Either, therefore, the reality which underlies space must form a discrete manifoldness, or we must seek the ground of its metric relations outside it in binding forces which act upon it. And then we have his finale here. The answer to these questions can only be got by starting from the conception of phenomena which has hitherto been justified by experience and which Newton assumed as a foundation, and by making in this conception the successive changes required by facts which it cannot explain. Researches starting from general notions, like the investigation we have just made, can only be useful in preventing this work from being hampered by too narrow views, and progress in knowledge of the interdependence of things from being checked by traditional prejudices, which is a mouthful of saying, hey, you could probably delve into questions that sort of come up from this framework of thinking that he has described in the last dozen pages to look at the foundations of space and time that Newton used. And you might find interesting things there, is basically what he's saying. It might be a worthwhile... Oh, my cat's getting food. And it might be a worthwhile endeavor. I'm pretty sure that Gregorio Ricci Curbastro and Tullio Levi-Civita directly followed up on that. But they basically did that mathematically by working out tensor calculus, Ricci calculus, absolute differential calculus. Because then Einstein would be in correspondence with Tullio Levi-Civita, and Einstein would be asked things like, what do you like about Italy? And Einstein would say, I love two things, spaghetti and Levi-Civita. Like, oh, this is the night. Okay, we get it, bro. yeah, this leads us into the domain of another science of physics into which the object of this work does not allow us to go today. But I was like, dang. Riemann was like ready to follow in his father's footsteps to be a pastor as well, study theology in university, ends up doing math, still comes out with this, and obviously his personality is shining through. He's not really, he doesn't really have the gift of the gab, let's just say. He's living in the recent shadow of people like Hegel on the academic scene. His advisor is Gauss, but nonetheless, he has this, like, you know, we now know that there are huge implications for Riemannian geometry in modern general relativity, but it's like, dang, man. So, anyways, tears to my eyes. Anyways, we haven't even gotten into the equations, bro. Okay, well, maybe we're just gonna be moving on. Oh, here's the boy. We're gonna go full webcam to show this little man. Oh yeah. Get over here. Oh yeah. You just had a nice dinner. We're not gonna go full webcam. Here we go. Yeah, there we go. Would you like to see anything? Alright, I just had to wait for my cat to not be interested in sitting in front of me anymore. Okay, here we go. So, curvature, this isn't really curvature, this is maybe arguably still within geometric context, but where I'm going to take it is into curvature. So, recall the first fundamental form being presented as ds squared equals e du squared plus 2f du dv plus g dv squared, where E, F, and G are metric So, yeah, I guess if you gathered anything from my rant previously about doing dot products of these smallest, well, I guess it would be the largest of, the largest of rulers that are too small to be relevant for measuring lengths on a surface that you care about, basically. That's like the real world empirical, like trying to nail down what these ds, du, dx, d whatevers are. So the ds squared, though, is just on the surface. Maybe don't think of s as standing for surface, but s usually represents, in my mind, something like arc length on that surface. more formally. Then we have du squared, and then du dv, and then dv squared. Then we have these metric coefficients, not necessarily scalar, not necessarily constant, but yes, we can say but if we're thinking about stretching a surface or a manifold that has this ds squared metric, a metric that can be put in this form, then if we had constant scalar scalings of E, F, and G, that could possibly amount to a conformal dilation, which would be stretching. Also, feel free to jump into the comments section if I say something wrong. I'm going to try to not edit out as much of my just off the top interpretations, opinions, reactions, and so on, as I kind of do when I'm editing previous reading stream episodes, if I'm being honest here. Anyways, Gaussian curvature. I will often refer to as K. Amounts, deforming K amounts to bending. So I guess this K, why not? We'll just say kappa 1, kappa 2 equals R Yeah, this is the definition, I guess you could say, from the back of the Kreyszig Differential Geometry book. Gaussian curvature capital K is equal to the product of the principal curvatures, which are denoted as kappa, usually kappa 1, kappa 2, which is equal to capital R, which is the Riemannian curvature tensor, as denoted in this book. But at this point, you could be like, what does that even mean? It's just a capital R, sub 1, 2, 1, 2. That doesn't mean anything to me. All over G, which is the discriminant of the first fundamental form. So it literally would be like the discriminant of the above, that E du squared plus 2F du dv plus G dv squared. Discriminant of that. That is what's on the bottom. So that is also equal to the discriminant of the second fundamental form, B, over, again, the discriminant of the first fundamental form. But those second two, it's kind of like, what does that really mean? But we will see here in a little bit. We're gonna have a little bit of this going on. You know what I mean? We're gonna... Whoops. Got a little bit of this. Actually, you know what we'll do? We'll make this nice. We'll do this the right way. We'll hit him with the begin align. We'll do an align star, pull this in here. Boom. Some of you at this point might be saying, well, Anthony, in another episode, you did this all with the terminal and you just compiled directly, and that's the real way to do it. What are you doing on a Mac? What are you doing using TechMaker? Well, yeah, you're right. Sometimes I use Linux machines. I'll use, Ubuntu for work, or for honestly like CUDA drivers. Sometimes I use that the Uniboomer ThinkPad stripped down, GNU, free, Richard Stallman, open source, right? But right now, I'm trying to be creative and use OBS, so I'm using TechMaker. But I want to do this so that you guys can also see what's going on. Anyways, let's align. Yeah, that looks alright, I guess. We're going to see this in a little bit. G times K. Scaling. If we have, let's say, the flat metric is G, ds squared equals du squared. It's just nothing. Flat. Well, then we have non-zero but constant K. Scaling that. We put that into a tensor, we call that the Riemannian curvature tensor, right? So that's what's going on here. We're going to do a little peek into the future, though. Ricci curvature. This, I think, gets brought up in chapter 8 of Differential Geometry, but it's like, obviously, we've realized the jig is up. We've been the butt of the joke. We've been reading basically watered down elementary basic Riemannian geometry for a few chapters now. We've been calling it differential geometry. Let's just make this concrete here. I have been slacking in the topology and the smooth manifolds department. So it's like, why should I even continue going further into Riemannian geometry? I probably already said that. Well, I hate to break it to you, but I already went even further, and I looked into books like Peter Peterson's Riemannian geometry, and I found topics like this Ricci curvature here, and there's levels to this game, my man. There's levels to this game. The differential geometry game. I was so cringe when I first called it differential geometry squad. Squad that just, it's just like nails on a chalkboard, you know what I'm saying? It's like differential geometry gang. That just sounds good. We're not in differential geometry right now. Anyways, getting back to this Ricci curvature. R with two subscripts, I and J. Okay, in the above, we've got Riemannian curvature tensor, supposedly a component. 1, 2, 1, 2. We've got 4 indices that we need in order to specify elements of the Riemannian curvature tensor. We're looking right here. Ricci curvature, just 2 indices, R, I, J. That is a trace of the Riemannian, the Riemannian curvature tensor. Question mark, someone in the comments. shout out if you've made it this far, first of all. But then if I just made a mistake and you're still watching, now's the time to comment calling me out. But I'm pretty sure that that's the right way of maybe saying it, because what we're going to be doing is a tensor contraction after deriving a Riemannian curvature tensor form, let's say, where we've got 4 indices. We're going to crank it down to 2 by doing a tensor contraction, because, you know, maybe I haven't explained this well enough so far. I'm going to start with Christoffel symbols, which then allow us to form the Riemannian curvature tensor. We do a tensor contraction on that, and we're going to get a form known as Ricci curvature. But what's more interesting is that this is going to result in a partial differential equation, which is of the form of what I already mentioned, that metric for isothermal coordinates, let's say. That, when you look at that metric for the isothermal coordinates, that is a PDE known as Liouville's equation, but that drops out of calculating Ricci curvature. We can simplify a little bit by just like knowing, or kind of like not guessing, but it's like we're going to go with the form of stereographic projection. We could use these things called, I guess, like Werdinger derivatives, which is like, okay, we take our Liouville equation, we're going to do complex analytical function stuff with this. So when we have complex derivatives, right, we can make the math work out easier, and we shake it up and we get this whole logarithm of the stereographic projection. Because it's like, if you use complex analysis, complex geometry, it's pretty easy to come up with the stereographic projection formulas. And then it's like, you know, if you're doing, it just so happens you're doing this PDE, it's like, you know, you could choose to not do it in complex variables, but then if you do, it just so happens that, you know, the logarithm of the stereographic formula, which then invert logarithm, you get exponential, which is like, duh, complex analysis, exponential function, duh, right? That's just like, obviously, in differential geometry game, we know these things already. Anyways, so I mean, I've already jumped pretty far ahead here with my last ramble there. Yeah, I took the time, you know, making this figure here. I could have drawn this out on a tablet and pen, tablet and stylus, if you will. Could have drawn pen and paper, scanned it in. I decided to use good old faithful MATLAB. And I tried to take heed of some of the lessons that I have learned over the years with making figures, as far as labeling, not making it crowded, making lines bold, titles and everything, legends. Okay, this is the point. I wanted to do this right. It was kind of like I said towards the beginning. If you have, in 3-dimensional space, unit sphere, x squared plus y squared plus z squared equals 1. If that sphere were your head, and you cut straight down the center line of your face all the way through the back, and then separated the two halves like your head was a piece of fruit that just got cut in half, and then you're looking at the cross section of the inside of that piece of fruit, that is the graph that you're now looking at of stereographic projection. So basically, the x-axis is the complex plane going into the page or going into the screen. It would be like if you shot arrows with a bow and arrow all along the x-axis there, you would that's the complex plane that you would get there. There's a circle, negative 1 to 1 unit sphere. Obviously, the north pole is labeled N, and we've got our projection point P. This could be defined tomato, tomato, say, oh, we're going to project from the North Pole through a point on the sphere. Where does that project onto the plane? Or you could say, what is the projection of the point on the plane onto the sphere? It's more accurate to say the second one, because when you really think about it in this whole stereographic projection complex sphere thing, the North Pole is the point at infinity. So you can't really be at n projecting through the sphere, you know what I mean? It's more like if you were infinitely far away from the sphere, then you would project that p underscore point would be closer and closer to the North Pole. So that answers that question if you had that in mind. But anyways, so we start off anyways under that convention at the point P on the x-axis as depicted here. Project a line through to the North Pole. The point on the sphere is P underscore, and that point is above, directly above P prime in the complex plane. So when you look at this, realize that P prime is equal to a complex value x plus iy. And P underscore would just simply be the whatever that x and y from x plus iy. Take that x and y and then just be like at coordinates x, y, z, that's what P underscore is. So I'm just going to work this out right here. The point P underscore so P is projecting okay, so I guess at this point we need to make a geometric realization. So start out by looking at the triangle from P to the origin to N. Now the distance 0 to P could be anything, because we could allow any point in the complex plane to be projected here. But 0 to N, by defining this to be the unit sphere, is equal to 1. And I really screwed myself over, because in my notes, those lowercase p's are in my work lowercase z's. Okay, the problem is that when I was doing my work, there's a mix of lowercase x's, y's, and z's, and then capital X's, y's, and z's. And then I figured, okay, instead of doing lowercase z on the MATLAB, I'm going to use the letter P. I'm going to change this right now, but if you watched up to this point, then watching this change right now, boom. Now we're all on the same page, and I can just keep using my notes here. So as I was saying, we have to come up with this geometric realization. This is a statement about the similarity of the triangle ONP and the triangle PP prime P underscore, or as we're going to call down here, Z prime Z underscore. But then the magnitude of Z is this ON length, and Z prime is this P prime to P underscore length. So because you can see, another way of saying that these triangles are similar is like you could slide this P prime P underscore triangle inside the ONP triangle, and they're both right triangles, and so we can algebraically describe these triangles' similarity by saying, okay, the magnitude of this ON leg of the triangle, the outer triangle, let's say, we can call that lowercase z in this expression, and then the length of p prime p underscore, that's z prime here. So the ratio of these, well, because this is a unit sphere, that z magnitude is 1. And then because this p underscore is at the point x, y, z in coordinates, then if you have 1 here and you subtract z from it, that's how you come up with these ratios right here. So from this, I'm going to have to do an align. I forgot. Begin align. This is going to be a long video at this rate. So I'll just do that. Okay, so now we're going to compute Okay, so we're going to compute now. Okay, we looked at these triangles that are similar. We came up with this ratio of the lengths of sides of these triangles. We express them in complex variables so that we can just write 1 over 1 minus z. We multiply this magnitude of z prime over to the other side, and then we just, instead of saying magnitude of z, we just say x plus iy equals, and then for this z prime corresponding to how we defined z underscore z prime and z, I kind of jostled around with the whole p and lowercase z here. Sorry about that, but anyways, x plus iy equals capital X plus I capital Y all over 1 minus capital Z. We compute the magnitude of the left side, which if we just realize, okay, well, x, y, and z on the right-hand side, the capitals are scalars, and so we can just simplify the whole x plus iy Pythagorean theorem, and then simplify things out. That was a mistake, a typo. Got the 2 there. Okay, now we've got x squared plus y squared over 1 minus z as a quantity squared for what the magnitude squared of this lowercase x plus I lowercase y is. But we notice based upon the unit sphere x squared plus y squared plus z squared, or Pythagorean theorem in 3 dimensions. So we're bringing up the Pythagorean theorem again, but in another way, as we did from 2 lines previously. We can algebraically manipulate that around, so we have x squared plus y squared equals 1 minus z squared. So what we had just computed can now be rewritten as 1 over 1 minus z. Okay, so we okay, so we can go back to this line up here, and we can reinterpret or rephrase the geometric insight as saying if you take the ratio of the lengths of those two triangles that we see in this cross-section of stereographic projection, take the ratio of ON, where O is the origin and the north pole of the unit sphere, and P prime to P underscore, or Z prime, lowercase z prime to lowercase z underscore. Compute the ratio of those, but then if you multiply that ratio with the length lowercase z prime, then you'll get back the length of ON. Okay, I guess okay, I guess we could take this one step further as well. Wait. Oh yeah, we need one more insight before we go further off of this one, which is that oh yeah, snap, okay. Yeah, which is that if we square this, then we get Alright, so I might as well. Whoops. Okay, so we have our algebraic phrasings of the geometric interpretations that I may have hammered to death by now, or maybe have not hammered home enough. But we used the similarity statements to come up, or the similarity statement that's like the key geometric insight, if you will, to come up with two new statements, where we look at this ratio as a way to scale any particular triangle vertical length from whatever point is being stereographically projected. How can we scale that back to the unit sphere, or the projecting sphere radius, essentially, which is what's implied by lowercase z. We also have that if we do the ratio of the squares of the magnitudes of these triangle lengths, we could have this representation which is 1 over the square of the quantity 1 minus capital Z, which then at the point where our calculations are so far, we're going to use that in tandem with how, again, being that this is in the complex saying, we have x squared plus y squared is the magnitude of the z prime squared. Okay, so I did a little more rearranging here. So we're basically computing out how we now have the magnitude of this z squared. So the square of the magnitude is equal to this fraction 1 plus capital Z over 1 minus capital Z. basically the goal of the computations from here is now to manipulate this square of the magnitude of lowercase z equals the fraction 1 plus capital Z over 1 minus capital Z into a statement of capital X plus I times capital Y equal to then lowercase x and y somehow algebraically put all together in pieces. So we have that on the left hand side, and then, like I said, the capital X plus I capital Y on the right hand side. So I'm just going to type this out. Alright, so just computed what I said I would, and the thing to realize here is that we can now factor out on top and we can also realize Yeah, if we just increase the number of dimensions and we just extended out x squared plus y squared, had more letters, essentially z squared, or you could just do x1, x2 all the way through n, then we can see how we're starting to get we've calculated the first stereographic projection formula, how we're starting to get close to the expression in Riemann's habilitation thesis. So I think we can also compute that. I kind of got lost in this part of my notes because, to be honest with you, I did everything that I described as far as like Christoffel symbols, Riemannian curvature tensor, Ricci curvature tensor, Liouville equation, substituting in the stereographic projection formula as a solution, connecting it all together with Bernhard Riemann. I did that first. And I was like, well, might as well slap on a construction of the stereographic projection formulas. And I believe that at this point I got the one that I needed above with that whole 2 times quantity x plus iy all over 1 plus x squared plus y squared. There's 2 stereographic projection formulas, and I think that this is the other one from my notes. Otherwise, it's yeah, that's another formula, but I don't know, so I guess we might as well just start doing the whole Christoffel symbols, etc., and then getting all the way down to the results of filling in the blanks. So, yeah, I guess to recap over, what was it, the last hour? Wow, so this is 2 hours already? Yikes. Okay, so, well, at least at this point we've gotten to deriving stereographic projection formulas, and then now down here at the bottom of this outline we have what we're aiming towards. So would you look at that right there? We might as well just slap a label on this one. Yeah, so we can see the similarity in form between line 6 and line 7 here, and we're going to fill everything in section 5 and section 6 here. So Maybe that's a good way of putting it. Our motivation is to demonstrate a solution of the Liouville equation given constant Gaussian curvature, which we're going to call K. We consider constant Gaussian curvature so that the locally Euclidean metric of the manifold we're considering overall in our mathematical context is scaled by a conformal factor. And I wanted to use a fancy word here that I learned recently, which is ansatz. Ansatz is an assumption about the form of an unknown function which is made in order to facilitate solution of an equation or other problem. So I've kind of already alluded to this, but we're going to almost messed that up big time by having the lowercase deltas. So we start off with the general Louisville equation. We have this Laplacian of the log of our conformal scaling factor function f. Or no, f is our metric that we're looking for, and this is equal to negative k. That is our conformal scalar factor, which is curvature. K is the Gaussian curvature, and then that's times the function squared. We do a change of variables, log f, so that now we have just the Laplacian instead of Laplacian of a logarithm on the left-hand side. That is equal to negative k times exponential 2u. We describe our conformal scaling by curvature as ds squared equals e to the 2u, then times the sum of our dx squared, with u being in terms of x1 through xn, but we also sometimes will write that as u in terms of r, where r is just, again, going back to the Pythagorean theorem. That's all that is. We seek the form of our unknown function u in this PDE here, but in earnest we're going to effectively end up computing e to the 2u. And how are we doing on time? I've done this for 2 hours and 15 minutes. We're going to do another break. Let's do it. Alright. To think that this is only the preamble. We are only now starting to get into the nitty-gritty. Let's get into it. Okay, so I guess maybe I'll start here. Consider the first fundamental form and its discriminant. G sub alpha beta equals how about that? We'll even just say, consider a component of the first fundamental form. G sub alpha beta equals the dot product of x sub alpha and x sub beta. Let's, for the moment, limit to just 2 dimensions and say that we only have whoops. So let's for the moment limit to just 2 dimensions and say that we only have x1 and x2. So then the discriminant of the first fundamental form would be let's just start this on a new page. So okay, so if we're just limiting to 2 dimensions just for the sake of this definition of the discriminant of the first fundamental form, then the so-called discriminant of the first fundamental form would be g sub 1, 1 times g sub 2, 2 minus g sub 1, 2, then squared. Now, I said just for this, we're limiting to 2 dimensions, but now we're going to open things up because now we're going to define Christoffel symbols. All right, so this is now a formula of how we can relate partial derivatives of the components of the first fundamental form, which, again, we actually went over that earlier where we have this, where is it? Yeah, ds squared equals capital E du squared plus 2 capital F du dv plus capital G dv squared. Okay, now we were looking at the first fundamental form as these components where we have g sub 1 1, g sub 2 2, g sub 1 2. That's just for 2 dimensions. We're thinking generally now, and we're doing derivatives of components of that first fundamental form, because then to really touch grass, those components are how we're building the metric on these n-dimensional Riemannian manifolds that have constant curvature. Alright, now I'm going to type out here some transformation laws, which, as you'll see, it's what it sounds like here, raising indices and lowering indices. Keep in mind that this Christoffel symbol is not a tensor, but we can almost think of with this notation that there is a kind of raising and lowering indices thing going on here. Yeah, so going back to the tried and true Kreyszig differential geometry, we have on page 141 here, back in section 45, which feels like forever ago. We are at over a year, though, because I think I uploaded episode 0 on like the 8th or the 12th of February last year, and then it's like the 25th of February already, so cheers to that. But anyways, at the bottom of page 141, we mentioned that the Christoffel symbols do not form a tensor. So like I said, they're not tensors, and in tensors, we're going to be dealing with one in just a moment here when we do a contraction. But yeah, this is kind of like a transformation law. Anyways, I'm just going to get to typing. Less talking, more typing. Alright, so here we are. Listen to these little transformation rules, raising or lowering indices, if you have it, for these Christoffel symbols, which now I've said like 4, 5, 7 times now. These are not tensors. We're multiplying by essentially the first fundamental form, and yeah, we might as well just get into it. We are going to start calculating with what is called the mixed Riemann curvature tensor. And okay, still, so far, we're going to take stock here. I feel like I'm in a time warp when I'm filming these, because it could be like 20 minutes of filming turns into 10 minutes worth of video. And, you know, videos could be hour and a half, hour and 40 minutes long. We haven't had a 2-hour long video yet. This might be one. And so 10 minutes, well, when I'm watching YouTube, sometimes there'll be videos that are 10 minutes, if that, and that'll be like a long video, 10 minutes. But right now, you're probably watching a video that I've chopped down to be like 2 hours. If this video right now is less than 2 hours, that's probably a miracle. But anyways, I'm going to take stock once more here. We have our context. We're looking at constant curvature, n-dimensional Riemannian surfaces, and we've started to phrase that then in explicit mathematical statements, which has included a construction of the stereographic projection formulas, which are going to come into play into the solution. Solution to what? Pose the problem here from our privileged modern vantage point. We can say, oh, we're going to be looking for a solution of this nonlinear partial differential equation called the Liouville equation. And we're going to compute what's called Ricci curvature. And, well, why is it called Ricci curvature? Well, it's named after Gregorio Ricci Cubastro. Well, it just so happens that guy came after Riemann. So how could it be that we're trying to fill in the gaps, fill in the blanks, you know, do the whole left to the reader as an exercise thing with the one mathematical expression in Riemann's habilitation dissertation? How are we going to do that using something that's basically from the future of how did he come up with? But really it's just so that we can keep the structure of what I'm typing here in somewhat of a like tractable logical order. Now we're actually getting into solving it, and we can see down there at the bottom, it's always going to be staring us in the face, basically, the result that we're trying to go for. Everything that I've pulled out of thin air, basically, for section 6, solving the problem, it all came out of the formula sheet in the back of Differential Geometry, okay? So, and then, you know, as long as we have enough wherewithal to say, okay, this capital gamma, which I keep on calling Christoffel sub alpha beta gamma, etc., is not actually a tensor. We need to have that kind of awareness so that we can do meaningful calculations. So one more thing from the back of the formula sheet, and then we're really gonna kick off into what for some people might be a mathematical notation nightmare, but we're just going to charge headfirst into this. Alright, here's a useful note here. Scalar curvature comes from the Ricci tensor, which requires the Riemann curvature tensor, which starts with Christoffel symbols, which are connection coefficients. And we could really go down the rabbit hole of what is a connection, affine connections versus metric connections, and look at connections between tangent planes on different parts of a sphere. We don't have time for that. I mean, we do, and I kind of just alluded to like all the major high points of that, and you can obviously Wikipedia that, but okay, and another thing I need to add to the ansatz. It's like this has been super chaotic, but going back to Riemann's actual primary source document here, we look at determining your position, let's say, on one of these n-dimensional manifolds. And, oh boy, here comes my cat. And when you're doing that, you will need, of course, in n dimensions, if you sum up 1 to n, you get this 1/2 times n plus 1 here, right? And then if you really think about it, well, what if you sum up to n minus 1 instead of n? So, you know, obviously you just get this 1/2 n times n minus 1. I forgot that I need to add here Oh, my cat's gonna attack my hand. Alright, I'm back. I just had a little meal of rice and ground beef. If you want to know what it looks like when I cook ground beef, check out episode 24 of my Differential Geometry reading streams. Anyways, we are back, and I remembered there's one more thing that I have to add to the ansatz before we dive into some deep, extensive basically by hand mathematical calculations here. So we need to add an ansatz here. Our choice of metric scales the flat locally Euclidean, or maybe we could even say Pythagorean, or maybe that's too restrictive. My intuition makes me feel that to call Pythagorean Euclidean that way is restricting the term Pythagorean. Anyways, metric by e to the 2u. Because now we're going to come down here and we're going to start computing the mixed curvature tensor. Let's just get it on for the metric. So, for the metric G sub ij, first fundamental form perhaps, Christoffel symbols are Christoffel sub ij superscript k equals 1/2 G superscript km times quantity. What? Yeah, partial I of G sub mj plus partial j of G sub mi minus partial m of G sub ij, closed quantity where partial I just denotes the partial derivative with respect to xi. So let's just compute some derivatives for the generic metric components. And of course, this delta here is a Kronecker delta. Alright, so just straightforward computations of easy exponential function derivatives. Alright, so now we're going to simply take the derivatives that we just calculated, substitute that into the Christoffel symbol expression that we have in line 11 here. We're going to go from there. Alright. So now we have Christoffel sub ij superscript k is equal to, whoops, 1/2 times, doesn't make sense. Good thing I read this back. 1/2 times e to the negative 2u, then times delta superscript km times the quantity. 2e to the 2u times partial I of u times delta sub mj plus 2e to the 2u times partial j of u times delta sub mi plus 2e to the 2u partial m of u times delta sub ij closed quantity. And of course we can simplify this up a bit, cancel out the exponential. So again, here we have Christoffel sub ij superscript k equals Kronecker delta superscript km times the quantity partial I of u times delta sub mj plus partial j of u times delta sub mi. Good thing I read this back. Plus partial m of u times delta sub ij. It's another Kronecker delta. Alright, so now using the transformation law of Christoffel symbols, wherein delta superscript km times delta sub nj equals delta sub j superscript k, we now get the following. We're going to compute a few things. It's basically copy-paste, but it's important in order to fill in all the gaps of the details. On that note, this kind of reminds me of Foundations of Analysis by Edmund Landau. And actually, this is a good one if you are highly autistic, let's say. I mean, no disrespect to people who legitimately have autism. I mean, I've known people, I had a stepsister who had autism, so I've seen it very up close because she lived with me and my sisters and my mom as well as her dad. We all lived together for basically throughout the time I was in high school. And, when I say for people who are autistic, it's more of people who are otherwise functioning in like society occupationally, and they can go to school and stuff, but it's that they just would probably relentlessly question foundational or axiomatic aspects of whatever you were talking about, and that would probably be especially true for discussing math with these types of people. That's what I mean by when I say autistic. We have here, this is something that I'll never forget, which is in the preface for the student for this Foundations of Analysis by Edmund Landau. To prevent arguments, a number, no number, two cases, all objects of a given totality, etc., are completely unambiguous. As if it was the first time that this guy Edmund Landau had ever been asked that question, those questions anyways. So, once again, we just used this transformation law of these Kronecker deltas. We're going from the form on the left in what we had calculated at line 13. We're taking this Kronecker delta transformation law to transform those Kronecker deltas into the form that's on the right-hand side of this expression here. And so that's what I've computed out here. And now I'm going to insert that back into line 13 essentially here. Oh, I don't even need any of this. As you can see here, we computed out all of the Christoffel symbols in terms of partial derivatives and reduced it down as much as we basically could. And now we're going to plug all of this into the mixed Riemannian curvature tensor, which, again, that was the last thing basically that we pulled from the formula sheet of our book we've been reading, Differential Geometry by Erwin Kreyszig. Let's get it. It's really hot. Alright, maybe now's a good time to talk a little bit. We will now insert what has been calculated thus far into the mixed Riemann curvature tensor. Now if you notice what I had above in line 10 here, this is with alpha, lambda, beta, and sigma. But now on line 17 here, I've just rewritten that, so now we have indices I, J, K, L, and M, and then we're going to be consistent that way with what we've worked out thus far. And so now what I'm going to be doing is just simply computing out all of the different terms that are in line 17 here using things like line 14, 15, and 16. So I'm just going to compute here one of these Christoffel symbols. I'm going to compute some derivatives, and then I'm going to compute the connection terms here at the very end. So once I have expanded all of that out, then we're going to take that, do a tensor contraction on that, and then we're going to have Ricci curvature. So let's plug and chug away. comes Mr. Boy. He wants to lay down. He wants to have another cameo. Missed a little. Excuse me, sir. Excuse me. My cat's making it hard. He's resting right on the trackpad. Okay, whenever I need to talk, I'm just going to pick this up here. But we're still going to have the ASMR keyboard mic going. I'm going to flip a page because right now I have expanded out everything to put back into the mixed Riemann curvature tensor here. Actually, looks like we're going to expand some of the Christoffel symbols a little bit further. So I'm going to type that out now. Also, don't judge my posture right now because I'm like half hunched around, cuddling my little boy while typing. Oh, he's got his hand on the mouse pad. Always trying to grab the mouse. Oh. Can't even hear you. I guess there's the ASMR mic, but... Oh my gosh, how embarrassing. I was just trying to type an ampersand and I didn't use an escape character before that. Rookie mistake. Alright, so now we have all the pieces. Not only like the formula sheet representation of the mixed Riemann curvature tensor, we took some of these derivatives a little bit further. So now I think I'm going to officially put it all together, and then we're going to sort of group the terms that we have into groups that we can sort of wrap our heads around what's going on with the entire, now expanded out, mixed Riemann curvature tensor that we're going to type out here right now. always falling asleep because I have a little cat boy laying on my arm right now, and it's 10:17, and I usually go to bed like 2-3 hours earlier than this, so I'm really up late past my bedtime. So I'm officially starting to compute the tensor contraction, and so I'm probably going to get up at like 3 in the morning and then finish this perhaps. We'll see how the lighting goes. And then I'm going to go back to sleep for another 3 to 4 hours, and then I'm going to wake up and go to work. Hopefully, so I've got 5 more pages of notes. Hopefully I'll get done with that, because we've got another hour of footage from this, and I'm not even done. So I have to stop now because I have to go to bed. So it'll be like nothing for you guys. See you in the next little clip now. Say goodnight. What's up, you guys? It is day 2 of getting the notes typed, of filling in the blanks. We started from things that are in the back of the formula sheet for Differential Geometry by Kreyszig. And then we are getting to this result here, which is in Bernhard Riemann's habilitation dissertation thesis, which is basically like a postdoc dissertation, if you want to think of it like that. But you don't do another dissertation as a postdoc. Anyways, yesterday I typed up, looks like 5 pages or so of filling in the gaps, and I didn't get nearly as deep as I thought I would. I mean, I bit off arguably more than I can chew, but we're going to get to the end here, so it's not like I'm going to eat the whole thing, basically, is what I'm saying. I don't know what that means, but okay, anyways, but yesterday I started off I said I started with the formula sheet in the back of the book, and then we're getting to the result in this paper that Bernhard Riemann wrote. Okay, well, maybe you just hit the timestamp and you came to day 2 and you didn't watch anything from day 1, which is okay. Okay, so the habilitation schrift of Riemann, it was only like 15 pages, and there was only one like mathematical thing written in the entire paper, which is this at the bottom here. It's like this expression, ds squared equals, in the numerator, the sum of all of the dx squareds. And then in the denominator, we have the quantity 1 plus alpha over 4, then times the sum of all of the x's squared. And then that entire denominator quantity is squared. And basically, that alpha is like this more or less floating parameter. And, you know, I've seen this coefficient in ways of like scalar over 2, scalar over 4, scalar over 8. But basically, it's just curvature, Gaussian curvature, which is if you have an n-dimensional manifold, let's say, then you need n-1 principal directions at most in order to specify the curvature at any given point. So like if you have a 3-dimensional manifold, then you would need 2 principal directions, and you define those to be the directions of the maximum derivative in each of those respective directions. Usually they're orthogonal to each other, but at any rate, you take the product of those principal curvatures, if you will. That's how you get Gaussian curvature. That is what we're looking at in the denominator here. So yeah, Bernhard Riemann, he is a very understated person, but is very profound. I think that's part of my impression that I get from just what I've read from his habilitation thesis. So there's 3 parts to the habilitation schrift that he wrote. There's the first part where he lays out what we now called a Riemannian manifold. He calls it like an n-ply extended manifold and refers to the properties as like the manifoldness of whatever notion of a manifold you're considering. And he specifically is diving into what he calls like magnitude relations and measure relations. So yeah, that's the whole first part of his habilitation drift. The second part is then where he's building up to basically classification result on Riemannian surfaces with constant curvature. And he doesn't really say that exactly. He kind of says something like flat manifolds are a special case of the constant curvature case, but that implies that besides the zero curvature case, which is flat, there's positive constant curvature and negative constant curvature. This coffee is still too hot to drink. My throat is just like so dry. Anyway, so I was like, how can I do several things at once? First of all, it's been about a year since I started doing the differential geometry reading streams, reading from this Kreyszig book here. And obviously I'm not all the way done, but I'm on like page 230 here out of 300 pages. So someone might watch my videos and say, oh, you know, you're just reading the words and you understand the notation, but you don't really know what's going on. I was like thinking to myself, if someone were to make that criticism, how could I prove them wrong? And so I was like, okay, one of the rigorous aspects of this book is how it deals with tensors. It goes into Christoffel symbols. It doesn't formally touch on like what we would call now like a modern definition of manifolds. Doesn't really go super deep into the topology. Some of these sections, like in chapter 6 where it goes into like the Bergman metric stuff, it's like we're kind of just getting like a feel for topics that Erwin Kreyszig was just interested in, just like aside from differential geometry related to his own main field, which at the time was arguably complex analysis. But I was like, okay, we're going to start with Christoffel symbols and we're going to actually compute out one of these tensors. We're going to do a tensor operation, which is a tensor contraction. That's actually where we're starting today. We're going to do a tensor contraction starting with the Riemannian curvature tensor, which we computed out starting from Christoffel symbols yesterday. And then that's going to basically result in a modern looking definition for scalar curvature. And what we're going to get is a form of a partial differential equation, which we're going to identify as being Louisville equation, which now we realize is related to isothermal coordinates on manifolds. So who would have guessed? But yesterday we also painstakingly derived the stereographic projection formulas, plural of formula, so that could be formulae as in the formulae of Frenet. We worked out the stereographic projection formulae using the model of the three-dimensional complex sphere mapping from the complex plane. That is going to be the solution in Louisville equation, or the Louisville equation form PDE that comes from the Ricci curvature tensor that we're going to get to. And by the end of that, we will actually have gotten to Riemann's result. So I'm just going to type. Yesterday, I feel like a good rhythm that I got into is I would type. That way it maximizes the keyboard ASMR typing aspect. And then I read back what I just typed, almost as if I'm reading straight out of a book like Differential Geometry, but it's what I actually wrote myself, right? And we're going to connect that way, fill in the gaps, what Riemann didn't show, because keep in mind, this is the only math in his entire 15 pages of a paper, right? And it's written in a very, I want to say like Hegelian German, because it's honestly it's a little bit muddled, but once you get into it, there's a lot of profound stuff. You know, he is very understated about his own philosophical contribution with this work here. Obviously, As a matter of fact, he did lectures that expanded upon this in the years immediately after this came out in 1854. But from what I understand, it wasn't until after he died that other mathematicians then fleshed this all out into the field of mathematics that we call Riemannian geometry. And yeah, there are definitely it goes back to where I was giving a recap of the whole entire Riemann's habilitation shrift, where the third section is actually quite profoundly philosophical, in that I think there's a profoundly understated hat tip at the very minimum to theology in a single sentence, which we might get into at the very end of this. And then there's basically a foreshadowing of going beyond Newtonian mechanics. So it's kind of like how I mentioned in that intro, is that there's the kernel of general relativity in the math of Bernhard Riemann's Riemannian geometry. So, all right, with that being said, I'm not going to clip this like I did at the end of this. Oh, and another thing is, I said at the end, I don't know if I edited it in or not, but I was like, oh, maybe I'm going to open up my setup and I'm going to finish this when I wake up at 3 or 4 in the morning. I didn't do that, but I really do wake up at 3 or 4 in the morning every single day. And then lately I do go back to sleep. Sometimes I time it where I go to sleep and then I get a full 8 hours of sleep before I wake up at 3 or 4 in the morning. So it's yes, that means sometimes falling asleep at 6 or 7 in the evening. I feel it's basically the way some people would stay awake late at night. I just kind of like to put that in the front of the day, basically, because it's unhealthy to stay up late, but it's kind of the whole idea of not being isolated in that I am necessarily what's the word for it? Pathologically antisocial or anything like that. I mean, maybe some people might argue that, but it's I really do cherish the connection and relationships with other people. So I'm not completely antisocial. I'm just highly disagreeable. But it's some people stay awake really late at night because they don't want there to be just a ton of other stuff going on out in the world when you sit down and you're I don't know, writing a novel that you're working on or something like that. It's the same kind of idea as that, but I just kind of like to get that by waking up early in the morning. And it's sort of if you're staying up all night, I feel 3 o'clock is a good marker that you've made it all the way through the night, basically. So it's why not just be awake at that time? And I'll just be awake then, and my cat will I'll sit upright, and I wear the really tinted blue light glasses, of course, and I really don't get on my phone, but I'll put on a guided meditation tape or something like that, and my cat will just sit on my lap and he'll just look outside here, and that's really nice. And I'll just kind of sit and meditate for an hour, and I'll just sit there and think, or maybe I'll open up my voice memos on my phone and I'll just rant for half an hour. But I didn't end up actually opening all this up, but I go back to sleep for then another 3 hours, and then it's boom, I can just I don't have a long commute to work or anything like that, and I'm just anyways, yeah, let's get back to this. Goodness, that coffee's starting to warm up my upper trachea here, so I'm not like out of breath like I smoke 2 packs a day. I don't smoke cigarettes at all. Just saying. Oh yeah, and if you're complaining about if I type slow, it's partly because I also want to make sure that I'm getting all of the indices and all of the notation correct. So it's not just like doing a freaking the quick brown fox jumped over the lazy dog typing WPM speed test, you know what I'm saying? So alright, so we're starting the tensor contraction, and now I'm going to add up all of these 4 bullet points here. Might as well just copy that one in. Why not? I haven't had coffee all day. I usually have coffee first thing. Well, not first thing. So like I was saying, how I'll wake up for maybe around an hour between like 3 or 4:30. Then I'll go back to bed for a couple hours, and then I'll be awake maybe at like 6:30, let's say, in order to go to work by around like 7:30 or 8. And I'll wake up, and I don't drink coffee first thing when I wake up, but I'll wait like 45 minutes to an hour. If not, I'll wait until I actually get to work to have the first sip of coffee. And usually I stop drinking coffee by about like 2, 3 in the afternoon. And so this is a real treat / bad behavior for me to be having a cup of hot coffee now at 4:50 in the afternoon. But you guys, my throat is so dry, and I just want to get this video out there because this is honestly why I haven't done a weekly stream, is because like it took a whole entire weekend to just get the math part of this like outlined start to finish, where I'm like, okay, I'm pretty confident that I've got this. And then to like get the parts like the stereographic projection part nailed down and all that, like it's really hard to work on this in just like the afternoons on weekdays. It really takes like a full committed effort on the weekend. But anyways, See, I was typing late last night, relatively late for me, because like I just said, I'm usually asleep at like 6 or 7, and then you can go back to the part 1 of this, which is from yesterday, and look at the time in the upper right hand corner. I was finishing like a little past 10 o'clock, if I'm not mistaken, so we're finding some mistakes. I'm trying to backtrack. I feel like I lost an L index going from the Riemann curvature tensor to where I am now in my notes. So I'm trying to figure out what's going on with that. Obviously I see the typo that's right in front of me, but that's not the problem here. Problem here is that we have this delta I superscript L, and then in my notes I have here delta sub I superscript K, which seems like a mistake. Oh, I get it, because part of doing the contraction is that we're letting L equal K. I was like, what is going on here? Yeah, because I just copied this line right here, and so now in the next line I'm going to write when L equals K. Much better for now. right here I did sum colon, and I really wanted to do sum exclamation point. But you know what, I'm going to go with exclamation point. Because yeah, now we're going to sum all of these worked out tensor contraction bullet points for, keep in mind, for the Riemannian curvature tensor, there were like 3 main parts, chunks. We call these like the linear terms, first quadratic terms, second quadratic terms. It's like, all right, we just typed out linear, first quadratic, second quadratic. Let's do this. See that? Already caught a typo. And now we're going to put it all together. So yeah, take a look at what we have calculated at this point. Oh, here comes my cat. Perfect. Whoa there. Look out, crazy boy. Alright, settle down, Mr. Boy. Excuse me, sir. Okay, right there. It's almost 5:30 and he gets fed at 4 and 6, and so he's probably feeding for a cat treat. Anyways, if you look at what we just calculated here, we have completed the tensor contraction on the mixed Riemannian curvature tensor. So we're down to a tensor with fewer indices now. We have capital R sub ij equals quantity n minus 2 closed quantity times quantity u sub ij minus u sub I, u sub j closed quantity. So keep in mind here that u sub ij means a second derivative once with respect to I and once with respect to j, where it's kind of like xi is a coordinate direction, xj is a coordinate direction. So then ui is just a first derivative of u with respect to I. Same thing for uj. Then we have plus Kronecker delta sub ij, then times quantity delta u, which is a Laplacian, keep in mind. Then we have minus quantity n minus 2 closed quantity, then times the magnitude of del u squared. So it's the square of the magnitude of del u, or that's a nabla, which represents the gradient. So one more time, that last quantity is the Laplacian of u minus the quantity n minus 2 times the gradient of u, and then we close off the final parentheses there. And you might say, well, how do we know if we are correct at this point? And I was trying to look for the formula in the PDF I have of Intro to Riemannian Geometry by John Lee, but I have a different edition than the physical copy that I have, and the physical copy has the equation, and the earlier edition, which I have the PDF for, does not. So maybe I'll try to scan this and put it in here, but this is on page 217 of the second edition of Intro to Riemannian Manifolds. I think the first edition is called something like Riemannian Manifolds Intro to Curvature, something like that. And then they renamed the title for the second edition. But it's the same book, kind of, because I guess they added in more stuff, obviously, including Theorem 7.3 on conformal transformation of the curvature, Let G be a Riemannian or pseudo-Riemannian metric on an n-manifold, capital M, with or without boundary, where the function, supposedly f, is in C infinity of M, so that's like infinite dimensional complex space on this M, well, an n-manifold called M. Oh my goodness. And G tilde is equal to e to the 2f then times G. So it's like, there you go, that G tilde equals e to the 2f times G. That looks a lot like the problem that we posed here, the Liouville equation, the isothermal coordinates, where we have the conformal factors scaling a Euclidean metric. Anyways, going on. In the Riemannian case, the curvature tensors of G tilde, which are represented below with tildes, are related to those of G by the following formulas. And then if we look at the third formula, we have capital S tilde is equal to e to the minus 2f times the quantity, capital S minus 2 times quantity n minus 1 closed quantity times Laplacian of f minus quantity n minus 1 times quantity n minus 2 times, well, we have the magnitude squared of this df, which is then sub g. But if we just look at that, that looks a whole lot like what we just computed out here after doing the tensor contraction on the mixed Riemannian curvature tensor. Keep in mind that we got to the point where we are in the notes here without consulting an outside reference such as Intro to Riemannian Manifolds. We did this all basically starting from the formula sheet in the back of Differential Geometry. I say basically because we also we divined the stereographic projection formulas from scratch basically when we had several geometric insights and we made the calculations nice by doing it in the complex plane or using complex numbers. Complex numbers making things simpler. Alright, so now I'm going to go back to typing and then I'm going to explain what I typed since we just got past a little bit of a milestone in our filling in the gaps here. Actually, wait a second. What I just said is a lie because I realized it turns out that we just haven't gotten to the part of the Differential Geometry Kreyszig book where we have what we just derived. So you might say that what I just did was a bit of a waste of time, but I would disagree because eventually I'm going to get to this section and I'm going to read it in one of these videos. And then I'm going to say, oh wait, I already worked this out without being guided by the text in episode 32, which you're now watching, because here we are in section 94 on geodesic mapping, and this is in the next chapter, technically, which is chapter 8. Special surfaces is what it's called. The big takeaway in my mind is minimal surfaces, which is technically still, yeah, it's differential geometry. It's part of smooth manifolds. But it's like really out of order because we just had chapters on geodesics, conformal mappings, and then absolute differentiation, which we're currently in. And then, as we've just picked up, we're kind of going deep on the Riemannian geometry. Okay, well, we have a Ricci tensor here. This looks like it could be possibly related, but it's like I said, judging by my reaction, being all candid right now, it's like, I don't know what, anyways, maybe forget that. But it's like, yeah, if you look at the scan that I put on the screen from Intro to Riemannian Manifolds 2nd edition, we're still on the right track here. So these calculations are correct, I believe. If you think they're wrong and you've been working alongside me and you found a mistake, let me know in the comments. hopefully you guys also appreciate that my voice has warmed up considerably more. I don't sound like a 70-year-old chain smoker, and typing a little faster, speaking more fluently. I'm a little more in the flow state here, and yeah. So yeah, now we just took the Ricci tensor, which we arrived upon taking a tensor contraction on the mixed Riemann curvature tensor, and now we have multiplied the metric through, which is conformal, as we've picked out, per the ansatz of this problem, if you will. We've chosen that to be e to the negative 2u. I went over that in the last part where the exponential function converges everywhere in the complex plane. It's analytical, that's why we call it that, and it really helps algebraically to have that 2 in the exponent, and also for our particular problem we're going to be having a log transformation involved in order to really get to the or at the core of this problem, which is this stereographic projection formula in the absolute banger Über die Hypothesen, welche der Geometrie zugrunde liegen. Yeah, I said that wrong the first time. I don't speak German. I have a horrible German accent. I'm not going to pretend to be like someone who was born and raised in the Midwest of USA, and then after getting a PhD goes to study abroad in Germany for the better part of a decade, and then you return to the States and you have this fake German accent. Like, okay, who are you trying? You're not fooling me, bud. That's just a broad generalization, not about anyone in particular. But, okay, so we're going to enforce some more specifics about our problem from the ansatz in order to dwindle down this statement of Ricci curvature a little bit to get at the specific Liouville equation form that we're going to compute upon in order to get our Riemann habilitation shift expression here. Alright, so when we consider an n-dimensional sphere, we have that the Riemannian curvature is equal to n times the quantity n minus 1, closed quantity, then times k, the Gaussian curvature. That is a relation that you could still glean from things in the formula sheet in the back of Kreyszig's Differential Geometry. And you can also, when you're reading Riemann's habilitation schrift, he kind of goes on a little bit of a riff about when you have an n-dimensional manifold, you only need n minus 1 coordinates in order to specify unambiguously a position on that manifold. And then I kind of like did a loosey-goosey argument of, what do you have when you do the sum from 1 to n, and then insert into that formula n minus 1, so you're effectively summing to n minus 1 instead of to n from 1, and just kind of dropping away the scalar coefficient. That kind of motivates, where do we pull this n times quantity n minus 1 from? And we just like plug that into the Ricci curvature statement that we have in, what is it here, line 52. And so we have all of the pieces here. We're going to do a little bit more as far as shaping our PDE with considerations from the problem. We're going to simplify the gradient and the Laplacian here, and then we're going to have something that we're going to start calculating upon with like a general stereographic formula algebraic statement of. So I'm going to type a little more here. Before I get into the further simplification, I figured I'd throw a little note in here about the Laplace-Beltrami operator, which is, I haven't gotten back to reading out loud in these streams the Kreyszig Differential Geometry book, but I last read section 74, which is on the Bianchi identities. Next section, section 75, is on the Laplace-Beltrami operator, and I show here that we can use that operator to restate the general form of Louisville equation here. And it's noted that in Lee's Riemannian curvature, Riemannian manifolds books, he does not cover the Laplace-Beltrami operator, and I couldn't figure out why, and that's because the Laplace-Beltrami operator is part of a subtopic of Riemannian geometry called Hodge theory, and that is covered in the Peterson Riemannian geometry book. So that's how I justify buying all these books, you know what I mean? So industry money, right? Kind of want to get rid of all of the mentions of we so that the existential point of view of this set of math notes that I've got here is more like a third person, objective, unbiased, reasonable observer, whatever that might be. But it's all good. These are just notes. Uh-oh, the menace is back. The dark menace. Say something. No? Okay. And I'm going to type this. Alright, we're going to shift to cat in the lap position. You guys, we are coming to the finale, the grand finale of calculations, where we're about to connect the dots and the gap will be basically filled, and we will have connected to, it's now referenced as line 62 here, which is straight out of Riemann's habilitation thesis, and we're about to get a calculation that connects to that. All right, and there we have it. So we start off with e to the 2u equals this general stereographic projection form, and we're going to try that as our solution, where we have a squared over a denominator of the square of a quantity b plus alpha times r squared. And now we see why we picked e to the 2u, because now we can square root basically what our attempted solution is. That whole stereographic projection form was basically everything is squared. So by writing e to the 2u, now we have e to the u equals a over a denominator of b plus alpha times r squared. And we're in the complex plane in a way, and so we can take a logarithm and we still have a complete function everywhere in our embedded, or I guess we would call it our ambient space. So now we have u equals natural log of a minus natural log of b plus alpha r squared. We're just doing some elementary school algebra here, or we could really say it's preschool algebra at this point in the year 2025. So now we have our gradient is equal to 4 alpha squared r squared over the square of the quantity b plus alpha r squared, u prime 2 alpha r over b plus alpha r squared, and then u double prime is equal to negative fraction with the numerator of 2 alpha times the quantity b minus alpha r squared all over the denominator, which is the square of the quantity b plus alpha r squared. And then we finally have the Laplacian. We have two different forms here, kind of for algebraic sake. The first one is the one I'll read for you here. Negative fraction numerator 2 alpha times quantity b minus alpha r squared all over denominator of the square of the quantity b plus alpha r squared. Then that first fraction is minus the second fraction with the numerator 2 alpha times the quantity n minus 1 all over a denominator of b plus alpha r squared. And so we use those relations for u, u prime, u double prime, the Laplacian and the gradient, to first approach the left-hand side of line 55 here, which is our PDE as far as we had taken it. So we calculate out the left-hand side, simplify. Thankfully, it dwindled down to something manageable. And we expand out the right-hand side, not much to expand, thankfully. And then we set these equal to each other, and we get closer to the solution in that we can determine that this a squared floating parameter we can set equal to 4. That's part of the solution. And we have some latitude here, so we're going to say, okay, well, we're going to pick for the other floating parameter of 4 for the sake of factoring, and we're going to do the same thing for this alpha here. We're going to pick it as 4k, because we could just leave it as, okay, here's our solution, e to the 2u equals stereographic projection formula, but we are trying to match the results in Riemann's work. And since we've gotten it this far and all we have left are these floating parameters, this is how you do it. Okay? So we're able to factor out, this is basically what math is all about, is after you've done all of this frankly excruciating heavy lifting of the computing, the plugging, the chugging, the algebra behind the scenes, you're doing the nitty-gritty, you're getting your elbows deep in the soil, you're doing that level of farming here, okay? And then you get this nice clean factor 4 out of the top and the bottom here, and it's just chef's kiss. E to the u equals 1 over a denominator of 1 plus alpha over 4 then times r squared. And wow, that's our conformal factor, because then you plug that back into our isothermal coordinate Louisville PDE here, and we have the result from Riemann's work. So all right, I think we might be in the final stretch now. I've compiled, obviously, the final copy for now, and I'm going to bust out the vlog camera and print it out for you guys. But there are more things to talk about in Riemann's habilitation thesis that I want to get to, particularly from the third and final section. So one more recap is section one of his habilitation thesis introduced what we might now call Riemannian manifolds. He called them basically n-dimensional manifolds. And then in section two, he had his breakthrough classification theorem of those manifolds when it is the case of constant Gaussian curvature. And then it's a very humbly understated section in section 3 where he's basically alluding to future applications in physics, basically the foundations of physics, Newton's physics that is, involving the assumptions regarding space and time. And now here we are in 2025, we know in the public at least that Einstein fulfilled that. And we're going to get into that in a sec, but I wanted to also point out here, this is from John Lee's Intro to Smooth Manifolds. This is literally, as you can see, page 1, chapter 1. We just go one page forward here, and we've got the we have the definition for a topological manifold of dimension n, which has the following properties. M is a Hausdorff space, so this is why we should all review topology. For every pair of distinct points P and Q in M, there are disjoint open subsets U and V, which are subsets of M, such that the points P and Q, such that the point P is in U and the point Q is in V. M is also second countable, which is that there exists a countable basis for the topology of M, and M is locally Euclidean of dimension n. Each point of M has a neighborhood that is homeomorphic to an open subset of Rn. And we go on a little further. The third property means more specifically that for each point P in M, we can find an open subset U of M containing the point P, an open subset U hat of Rn, and a homeomorphism phi, which maps U to U hat. And then the exercise, interestingly, is show that equivalent definitions of manifolds are obtained if instead of allowing U to be homeomorphic to any open subset of Rn, we require it to be homeomorphic to an open ball in Rn. That's the part I wanted to emphasize, or to Rn itself. Then we go on, topological invariance of dimension, coordinate charts. Now we have some examples of topological manifolds. We're going to go to example 1.4, spheres. Oh my gosh. What were we just talking about? Over here, figure 1.3, looking at coordinate charts on an n-dimensional sphere. Whoa. Example 1.5, projective spaces. I'm just going to read the beginning of it, and then we're going to get back into Riemann's habilitation thesis. We have example 1.5, the n-dimensional real projective space, denoted by Rpn, or sometimes just Pn, is defined as the set of one-dimensional linear subspaces of n plus one-dimensional real space with the quotient topology determined by the natural map pi, which is the real numbers, or which is n plus one-dimensional real numbers with the point 0 removed, mapped to Rpn, sending each point x in n plus one-dimensional real space with 0 removed. Or it's not 0, it's the origin. So I should say pi, which maps n plus one-dimensional real space with the origin removed, and continuing on to the subspace spanned by x. The two-dimensional projective space, RP2, is called the projective plane. And it keeps on going here. But then we can, of course, remind ourselves of how in topology, quotient maps, or just like the quotient topology, is a way to construct manifolds such as a torus, for instance, or the Riemann sphere in a way, because you're removing a point from a higher dimensional sphere, and then that gets, or no, it's like if you have a circle in a plane, then you're gluing that together into a sphere. That's what the quotient topology is. But anyways, that's a modern take. You have manifolds there, the three conditions: Hausdorff space, second countable, locally Euclidean. And then here we have the work of a reader left for dead to fill in the gaps of Riemann's Über die Hypothesen, welche der Geometrie zugrunde liegen, as an exercise. Introduction, geometric context, curvature, digression on stereographic projection of Sn. We pose the problem, we solve the problem, we start with things that we glean from the formula sheet of Differential Geometry by Kreyszig, the book that I've been reading out loud on YouTube for all of you now for over 30 episodes, for over a year now, for your viewing entertainment, listening entertainment, sleep-inducing entertainment, question mark? Okay, Christoffel symbols is what we started with. We briefly kind of like touched on the first fundamental form, mixed Riemann curvature tensor here. We just calculated away, crunched away, grinded it out for several pages. And then we started doing a tensor contraction. We just pieced it out. That's the key, keeping it organized, piecing it out, having notation where we wrote these partial derivatives, this u sub j, u sub k, instead of doing the whole partial symbol and then, partial u on the numerator, and then we have partial xj or xk on the denominator, that's atrocious. And then it makes it easier to make mistakes. So, the notation, keeping it clean helped. And then miraculously, we got to a statement of Ricci curvature without seeing that part of the book yet. That's like figuring out what the end of the mystery plot is of your, paperback mass market edition fiction novel, right? And then we scaled that Ricci curvature statement by our conformal factor, which is analytic exponential function converging everywhere in the plane, everywhere in complex space for that matter. Or you could think of it as a general polynomial when you power series that exponential out, right? That's, some of those bread and butter tricks of the trade in math world when you're out in the real world applying it up in engineering, I suppose, maybe, I don't know. And then we started enforcing conditions per our problem to kind of simplify our PDE up. Because once we multiplied our scalar Ricci curvature out, we have a PDE, and then we need to simplify that considering our problem. That way we're not just, we're not in the place of guys like Laplace just writing it down. Boom, that's all you got to do. Just kidding, that's not all he did. But basically, right, foreshadowing of if I ever get back to reading Kreyszig again for you guys. I will. But it's like, wow, this has been quite a detour. Section 75 is supposedly on Laplace-Beltrami operators, and you could kind of tie that in with forming our Louisville equation. It's just notation at that point because, as we can see, this is all of the real nitty-gritty, the hard work, the real heavy lifting in order to get solutions, in order to know what's right from what's wrong. Real talk. Finally, we did some stuff where we're equating a left-hand side and a right-hand side and finally picking what these free-floating scalars are, basically, and doing the mathematical ending where we just factor the 4 out, and it's like, holy smokes. Like, the whole time I was filming this, I started with a template that I wrote, and I put the result that we want at the bottom, and it's like, either we're gonna get exactly that or we're not. We got it. Über die Hypothesen. That's how we do it, I guess. So here we are in section 3 of part 3 of Riemann's habilitation thesis. And I've already remarked about this sentence. The questions about the infinitely great are for the interpretation of nature useless questions. And this whole time, I've already alluded also to how Riemann's father was a pastor. Bernhard Riemann, was originally going to go to school for theology and then ended up studying math instead. And I also brought up how lately, if you guys have ever heard of this guy called Lou Elizondo, he talks about with the whole idea of UAP disclosure that it's like a pyramid, a giant pyramid. And when you start, you're standing at the base and there are 2 opposing sides. I suppose this is a quadrilateral base pyramid, but you're on opposite sides at the base of the pyramid, and one side is religion, one side is science. And you think to yourself at first, being there at the bottom, that there's only whatever side you started on. There's only science, there's only religion. But then once you get closer to the top, you realize that they're closer together than you had previously thought, and ultimately that they depend on each other and in some ways are one and the same. And, obviously, right, like Bernhard Riemann, his life as a mathematician is another way to serve God. So we have this line there. And so I found we're just, going to be normal people, and we're like, okay, how did Riemann come to this? Well, obviously there's the text of the Bible in Western society. Like, we're thinking about this as philosophers, right? And we have the book of Job, and if we know the history of how the Old Testament came to be, it was basically where the people who wrote the Bible were at the fringes, the overlapping fringes of 2 different civilizations, basically the Mesopotamians and the Romans. And so like at the fringes of both of those societies, the intersection, that's where the people who wrote the earliest texts of the Bible came from, supposedly. And they weren't intentionally sitting down to write the Bible as far as what we think of it today as maybe this like cornerstone of religious institutions, this philosophical work, historical work for people, right? Like, they hang their hat on it spiritually, etc., etc. These people who were writing these early texts were like scribes, essentially, because this is in a society where not everyone is literate like today. And so scribes were the literate class of people. They were the only ones who would do all the reading and writing. And so the earliest texts of the Bible were written as like marginal notes that they kind of like passed around amongst each other. And so some of the early texts obviously have characteristics of laws, and some also have like a mythological storytelling, it's like a fable, or there's a moral to the story, if you will. And then there's also just factual history of tribes and peoples and nations and so on. So this is from the book of Job, where I'm sure you guys are familiar with this. This is, some would say, in the Bible, it's the critique of ideology, because it really just comes down to how Job views his situation, right? That's the whole key, maybe. But anyways, Job was virtuous and rich, and God gives Satan permission to strip Job of his riches, but Job is patient. Interesting that God gave Satan permission to do that. Some atheists would call that out right away. It's like, oh, the nature of God, right? Gotcha. 13-year-old atheist win. Put it on the chalkboard. The book goes on. God gives Satan permission to strike Job with ulcers from head to toe. Job is still patient. Job expresses the miseries of life, curses the day of his own birth. There's someone named Eliphaz who basically goes up to Job and says, God never afflicts the innocent. I'm going to change to webcam here. So it's kind of like saying, you must have done something in order to deserve this. And so Eliphaz says, you should acknowledge your sins, Job, basically. Job says, I didn't do anything wrong. He maintains his innocence, and he then starts complaining of his friends. So he once again declares the miseries of man's life, addresses himself to God. And then we have someone named Baldad. That's a name you hear all the time nowadays. Under pretense of defending the justice of God, accuses Job and exhorts him to return to God. And Job acknowledges God's justice, although God often afflicts the innocent. Job laments his afflictions and begs to be delivered. And here comes the part where we're tying it into questions of the infinitely great. This must be another one of Job's friends. Sophar reproves Job for justifying himself and invites him to repentance. Sophar the Naamathite answered and said, Shall not he that speaketh much hear also? Or shall a man full of talk be justified? I wish that God would speak with thee, that he might show thee the secrets of wisdom, and that his law is manifold. Get it, manifold? And thou mightest understand that he exacteth much less of thee than thy iniquity deserveth. How will you comprehend the steps of God, and will you find out the Almighty perfectly? God is higher than heaven, and what will you do? God is deeper than hell, and how do you know? And here comes the punchline. The measure of him is longer than the earth and broader than the sea. So, and then I just liked the line that kind of ended that chapter, which is very poetic, I think. The eyes of the wicked shall decay, the way to escape shall fail them, and their hope the abomination of the soul. So, kind of how I set that up, right? The book of Job, some would say philosophically, is critique of ideology. And in turn, leading up to that one line, which, if you're wondering, is Job chapter 11, verse 9. It's basically, Job is getting stricken by all this stuff, and his friends are coming up to him trying to give reasons. And Sophar is like, you don't know what God's plan is, might be like another way of putting it. But specifically, we have the measure of him is longer than the earth and broader than the sea. So this is the Old Testament. We're going to be complete here, and we're going to go New Testament now to the book of Ephesians, which is a letter of St. Paul to the Ephesians. This guy Paul, though, he was writing from prison, and Ephesians are the people of Ephesus, which is, as it turns out, you could call it a capital of Lesser Asia, or what that really means is it's an ancient city of modern-day Turkey. And I guess St. Paul, the way I think of him now is he's kind of like, because he's like 100 years after Jesus or something like that. So he's kind of like a guy who is a huge fan of Jesus, and he wrote a bunch of fan fiction about him that kind of just really took it to a whole new level. perhaps from, if there was a historical Jesus, perhaps. For me, the jury's still out, if you really want to know. But it's like, this guy Paul was a real person, and he wrote really intense fan fiction about Jesus, and this is one of them, because he's writing to these people who he converted for a few years. He, quote unquote, preached the gospel to for a few years, and then he's in prison, but he's writing to them. Interestingly enough, Paul was admonishing them to hold firmly to the faith they had received from him when he was preaching the gospel to them, and warned them against the sophistry of philosophers and the doctrine of false teachers who had come among them in their neighboring cities. Sophistry of philosophers. Keep in mind, the sophists, formally speaking, were like contemporaries of, say, Plato and Socrates and Aristotle, who believed epistemologically that truth amounts to rhetoric. So it's to say, if you had the gift of the gab that you could sway the audience in your favor, whatever you were arguing for, when that happened, that actually turns out to be what's true. And that's, of course, opposed to the take of Plato, which is that there is like a transcendental or an ideal, which is the truth or the form. Okay. But that's, we've already talked about that in these lectures. So these aren't lectures. This is not an audiobook. This is not a course. Anyways, we're in Ephesians. The target is going to be chapter 3, verse 18 through 19, but the book starts off, this is for context, Paul is saying stuff like, the great blessings we have received through Christ are so great. He's the head of all the church. All our good comes through Christ. He is our peace. Then we're in chapter 3. The mystery hidden from former ages was discovered to the apostle to be imparted to the Gentiles. He prays that they may be strengthened in God. So leading up to our target verses here, we have, I bend the knee to the Father, basically, that he might strengthen you, that you might be able to comprehend with everyone sacred what is the latitude and longitude, the breadth and depth, the sacred and the profound. To know also the benevolence of Christ, which surpasses all knowledge, that you may be filled unto all the abundance of God. So the target there was that you might be able to comprehend with everyone sacred what is the latitude and longitude, the breadth and the depth, the sacred and the profound, which is Ephesians chapter 3, verse 18. That's my translation because I'm going off of the Douay-Rheims Bible, which is like the contemporary of the King James Version, but keep in mind the King James Version is Protestant, which is what Bernhard Riemann was, of course. But I was born into a Catholic family. I don't consider myself like a practicing Catholic or even really like just Christian, period. I like to think of it more of or my own belief, maybe you could say, is like, I had my 13-year-old atheist phase and all that. But, I'm not in a Jewish family. I wasn't raised in an Islamic nation. You can't take back the years of my childhood that I spent watching VeggieTales, Silly Songs with Larry. I can write you an essay about answers to moral, philosophical questions, dilemmas, and things like that. You can't take away that I watched Silly Songs with Larry in my youth and then grew up around a bunch of people who, may or may not have been going to church, but are all supposedly Christian as well. So I think of it as like Slavoj Žižek said, Christian atheist. But anyways, the Douay-Rheims Bible is the Catholic equivalent of the King James Version. But I have a version that is side-by-side Latin and then the Douay-Rheims English translation. Anyways, so we had an Old Testament example of God is infinite. We had a New Testament example of God is infinite. But then, of course, one of the common denominational things of Christians is the textual emphasis of the Bible. Because, of course, for example, with Latter-day Saints Mormonism, the Book of Mormon then is contentious because Mormons consider themselves also to be Christians, but they say that the Book of Mormon is primary over the Bible in some respects. I mean, they'll never say it exactly like that, but that's what it amounts to, essentially, is the Book of Mormon is the primary religious, spiritual source document for them over the Bible. But the Bible is still important for them, as is Jesus. And like I said, the Mormons still consider themselves to be Christian. But anyone who's reading the Bible, or just like Christians will always be able to come back and sort and cite verses from the Bible. But there have already been, but in history there have been people like Thomas Aquinas, of course, or I mentioned even before Duns Scotus, or another one who comes to mind, St. Augustine and stuff. All of those guys that I just mentioned, yeah, they're like monks or theologians and stuff, but when you read their writings, even from a secular point of view, there are philosophical gems in there. And it's like if you had a time machine and you went back and you visited these people, you would inevitably come to find that they're intelligent, articulate, smart people. Sure, maybe like Thomas Aquinas had bad handwriting and all this kind of stuff, but like all of those people you would regard as smart people if you like met them in real life, essentially, right? So Thomas Aquinas I have right here. This is the entire Summa Theologica, unabridged in one volume. This is a massive tome where Thomas Aquinas set out to answer all religious questions, but basically he was doing it as like he's going at bat for God. It's like if you want to roll out any question to be like, oh, God doesn't exist, or whatever kind of question along those lines, maybe, Thomas Aquinas has an answer in the Summa Theologica. And in the first part, question 7, he actually answers about the infinity of God. And where I'm going with this is that he calls it 4 articles. So it's like there's the question. It's basically, is God infinite? After considering the divine perfection, we must consider the divine infinity and God's existence in things. For God is everywhere and in all things, so far as he is boundless and infinite. There we have it again. God is boundless and infinite. This is Thomas Aquinas, Summa Theologica. What did Bernhard Riemann say? In the extension of space construction to the infinitely great, we must distinguish between unboundedness and infinite extent. Coincidence? I think not. So that's like the setup, that's the question. And then there are 4 articles underneath that. So we have whether God is infinite, whether anything besides him is infinite in essence, whether anything can be infinitude in magnitude. Maybe that should be, I don't know, that's just exactly how it's written. And then 4th, whether an infinite multitude can exist. But interestingly in here, you may say, well, okay, Anthony, what is up with you're turning this into like, what do you call it? What do they call it? Some kind of like Sunday sermon, right? Is that what's going on here? Maybe, but in here, the answers involve geometry and math, as we'll see here. So, okay, we'll just break it down. First article, whether God is infinite. What I wanted to pick out here is a quote from John of Damascus, who lived from the roughly around the 6th to 7th century AD, and he was an Assyrian monk. And he said that God is infinite and eternal and boundless. So, very interesting. Second article, whether anything besides him is infinite in essence. For time, we're going to skip over that, but we come to the third article. Whether anything can be infinite in magnitude. I think that's what it wants to say, instead of infinitude in magnitude. This is basically written in just kind of like a dialectic or dialogue. I don't know if dialectic is the right way to put it, because I guess this is written syllogistically is maybe the right way of putting it. Each line is sort of like the proposition that the next line follows from. It's not quite a dialectic, like, Hegelian dialectic. But anyways, so the question in the third article, specifically on the infinity of God, is whether anything can be infinite in magnitude. So Aquinas answers, a body which is a complete magnitude can be considered in two ways: mathematically in respect to its quantity only, and naturally as regard its matter and form. A natural body cannot be infinite. An infinite body could not have any natural movement. An infinite body could not move, for it would occupy every place, and thus every place would be indifferently its own place. And then it goes on, it's basically like if you were infinite, then nothing could move, because there would be already something else in any of the other possible positions that your infiniteness could be in. So infinite bodies, Thomas Aquinas is like, nah. So he goes on, the same applies to a mathematical body. We must imagine in order for mathematical bodies to actually exist under some form, and so such a body must be implemented as some figure, and so would be finite, for a figure is confined by a term or boundary. And then we have replies to various objections. So this is Aquinas replying to objections, where if someone were to object to what his reply was, which I just read, he's like replying to those objections. I'm skipping the objections because you can kind of infer what they are for the sake of time here. Reply to objection 1. A geometrician does not need to assume a line actually infinite, but takes some actually finite line from which he subtracts whatever he finds necessary, which line he calls infinite. So it's like, if I'm going to draw you that stereographic projection figure from the beginning, the projection line from the point in the complex plane through the north pole of the stereographic unit sphere, the exact drawing line, yes, is finite, but then when we're discussing it, we're all agreeing that it is a representation of an infinite line. That's basically what Aquinas is arguing about there. Reply to objection 3. The infinite is not in the addition of magnitude, but only in division. Thank you, Thomas Aquinas. This is a very interesting metaphysical one that we could tie to quantum theory, but we don't have enough time to. Reply to objection 4. Movement and time are whole, not actually but successively. Hence, they have potentiality mixed with actuality. And now, here we go. We're going to wrap it up as far as Thomas Aquinas goes with the fourth article here, which is whether an infinite multitude can exist. So here we have our last Bible quote here, which is from Wisdom chapter 11, verse 21. And the chapters on other benefits of wisdom to the people of God. The verse goes, yea, and without these, they might have been slain with one blast, persecuted by their own deeds, and scattered by the breath of thy power. But thou hast ordered all things in measure and number and weight. Measure, number, and weight. So it's like, why are you trying to define a metric on a manifold? It's so that you can start defining length, angles, and area. Thou hast ordered all things in measure and number and weight. All kinds of things about math and numbers are said in this by Thomas Aquinas, and it's like, this is probably like 4 hours of raw footage at this point. We have things like, the species of multitude are to be reckoned by the species of numbers. But no species of number is infinite, for every number is multitude measured by one. Hence it is impossible for there to be an actually infinite multitude, either absolute or accidental. It's basically saying like God doesn't make mistakes, and the only way there could be an infinity of something is if God made mistakes, because God cares about everything that God makes, and so there can only be a finite number of things that God cares about. That's literally how Thomas Aquinas is saying that there's no such thing as infinite numbers. Literally, that's why I bring this up, is because it's like, oh, you can tell your aunt and your grandma that you're not going to go to church anymore, but, and it's also fair to say that church service is not very attractive or enticing for people to, like the standing and singing and all that just doesn't float the boat for a lot of people. But people are curious about things like infinite numbers. But then, you're not going to sit down at Thanksgiving and immediately pull this out of nowhere and say, how about it, Grandma? What do you think of how Thomas Aquinas thinks there are no infinite numbers because God doesn't make mistakes, kind of thing? But, you get these kind of curious one-off statements like the infinite is not in the addition of magnitude but only in division. Like, what's going on there? And then we also have here in a reply to the second objection for the fourth article. So this is again whether an infinite multitude can exist. Thomas Aquinas is saying, now there are various species of figures such as trilateral, quadrilateral, and so on. And as an infinitely numerable multitude is not all at once reduced to act, so neither is the multitude of figures. It's like saying, okay, well, you just said God doesn't make mistakes, so there can't be an infinite of stuff. That's cool how you said the infinite is not in the addition of magnitude, but only in division. Think of a triangle without any subjective properties. I've definitely brought that up in previous differential geometry streams. Trying to think of a triangle without any subjective properties, it's kind of hard, right? And that's to say, well, gotcha, Thomas Aquinas. That shows, because you can't enumerate all the different triangles that exist, there has to be an infinite possibility of triangles. And that's just on a Euclidean plane. Maybe all the triangles on Riemannian, blah, blah, blah. Okay, so, but Thomas Aquinas would say, exactly. You could spend the rest of the life of the universe drawing triangles. And once electrons and, oh my God, that was the worst brain fart. When electrons and protons finally all decay out to just heat, entropy, and whatever, all of the triangles that you drew to the end of the universe, those are the finite multitude of all triangles. So there's the possibility of there being an infinite number of triangles. But then Aquinas is being like, but God only made the finite number of triangles you made with your tedious life to the end of the death of the universe. And so it's like, yeah, you could start off in the kind of like cheesy, corny, boring Book of Job, Book of Ephesians. But there are some like poetic verses in the Bible still. And then you could take it through Thomas Aquinas and go into a very philosophical route that's kind of like, influenced or enabled by theology, right? And I bring all this up because that's what Über die Hypothesen, welche der Geometrie zugrunde liegen by Bernhard Riemann is all about. And yeah, see you guys in the next one.